Friday, November 5th. So here are the subjects, and I suggest we start right away by filling them in the Google Docs. So you have seen that there are many little items and number of items to the first. But check.
Oh, the microphone? Yes. Oh, we just got to take the same microphone is missing.
I may have occasionally took it at the Friday and then brought it back.
Okay. I'm sorry.
Thank you. So here is the link that I invite everyone to follow. Oh, I see already four attendees are there. So yes. Oh, you already got the rules of the game. I think it is quite quick. So you all have the. Oh, we should have 9. 1 for Lola, right? But still place your name tags near what you like, and
what date is it supposed to be?
I plan on November 5th. If everyone really wants to do it earlier, we can do earlier, but you like different day? You don't like Fridays?
Just the next week.
Oh, so all classes.
Next.
But we can prepare earlier, and then you just come for brief and verbalize it. But we can discuss it later and make a vote. So I will look on your votes by the end of the class, and if there are not enough votes, I will make some additional suggestions based primarily based on your preference. You can also type in if you have more than one choices, like just an example. Something like that. Or you can copy paste this little boxes with your names. Okay, yeah, thank you for doing it, and I'll continue with the class material. Ah, Nate, nice seeing you. So, do you have a computer on you?
Yeah.
Okay, so please plan on following the link and moving your name to the subject which you like it most. And by now I do not see a conflict, but if there are more than one person for one subject, I'll help to resolve. So the link is in the email with class notes. Okay. So I probably already declared that I hate homeworks, but we need to do 1 or 2 more, and let's plan to have it maybe in no, November 11th. From earlier year, it's too late. Maybe let's do it not coming Wednesday, but like in 10 days or in 9 days. And it's not challenging. It's more math exercise rather than actual physical chemistry. So I anticipate that you do it really quick, and I'll update these numbers and make some double credit for doing it earlier to match the class material, because some of this mathematical exercises will complement what we will be doing in class and make our class experience a little easier. Okay, so we are browsing in the space of models, methods, and right now we are approaching harmonic oscillator, which stands for several objects such as vibration of interatomic bond, vibrations of polar molecules in a solvent, and many examples that are hard to call chemical, but still related. For example, the multi-electron cloud in metal particle upon photoexcitation starts move all together, which is called plasmon, and they also obey harmonic law. So those all are referred to as harmonic oscillator because we assume that they oscillate with quadratic potential energy surface, and we are going through time-independent Schrödinger equation. We are trying to solve time-independent Schrödinger equation through concept of ladder operators, and as time goes by, we will try few other concepts from this list to this model. So some examples. I think it will be question number 6 for the coming homework. Like give examples of what can oscillate in nature. Competition. The more examples, the better. So, what are we doing, and what are our goals in this part of the semester in this chapter? So it's not fair. I'm supposed to speak and you're supposed to listen, but I think we'll have better connection. So maybe what is our goal
for this chapter? Trying to remember what it was.
Just find something with a solution, right?
Yeah.
Okay, that's good. Wyatt, I'm going to ask your help. How would you formulate what we're trying to accomplish?
You said oscillations already.
Yes, but you can tell more. Like, what is not clear about oscillations?
How we can model them
And why do we need to model them?
so we can understand,
Predict and interpret.
predict and interpret.
And practically, what we accomplished or what we are focusing now.
Focusing on using like the Hamiltonian.
Okay, so Hamiltonian enters into Schrödinger equation, and what is our expected outcome?
A future prediction.
On a long term, yes, but tactically, on a short term, what do we need as a important component?
The oscillation of the wave packet.
Okay, I'm absolutely happy, but on the way to the equation that is opened on the screen and on your screen, what it doesn't give any oscillations. It gives some less interesting, more technical information. What is unknown function in the equation that we are watching?
The R.
No. Phi.
Oh, phi.
How do you call it?
The wave function.
Okay. Good. Thank you. Well, I'm going to ask you any comments like why do we need to learn something about oscillations? Oscillations oscillate. Do we need to learn more?
To predict position of electrons.
But how can we speak about positions if they are uncertain, if there is a wave function?
If they are uncertain, is that what you said? Did you say if they are uncertain?
Yes, so it's expectation value of position. It's not position itself is not certain.
Yeah.
Okay. And what else can we get from the knowledge of the wave function or from the energy? Like this equation, we have two types of unknowns: phi, which is function, and E, which is energy. Why do we need to know energy for oscillations?
Why do we need to know energy for oscillations?
Which experiment may need them? Okay, I think Ramen is a good example. Does it say something to you? No. Sybil, did you do Ramen spectroscopy?
No, but absolutely.
Okay, let's just make our meeting vivid. So, can you tell are there any benefits from solving this equation? What how do you interpret what we are doing?
So basically, as White said, we have to know the wave function, and so we're trying to determine basically the wave function in order to determine the position of an electron at a given time. And in order to do that, right, we need the energy is important because we need to see how due to energy the electron is excited or from one state to the next.
Okay. Yeah. Thank you. I don't know if I will do the detailed. I will raising hand to say something. Yes, please.
So you were asking what experiment requires energy. So I mean, from what I understand, Raman spectroscopy has to do with light scattering. Just trying to understand how we use energy, how energy has anything to do with Raman spectroscopy.
Okay, I've got the question, and Joe, I apologize not to take an interview because I had enough input, but I'll ask you something during the as we go. Thank you all for making contributions, and special thanks to Sibel for trying to connect things together, and thank you all for bringing up the question about Raman spectroscopy, which is not major subject of our today's meeting, but if you do not discuss those things, it will be very boring math. It's better to make connection to real life. So when you have molecule, you excite it with light on certain frequency, and then you can the light can transmit through, can reflect back, can stay there and emit, or can emit immediately at slightly different angle. So not on a straight line, but on different angle, which is called scattering. And in addition, it is a little wonder why Raman got his Nobel Prize. The color of the scattered light will be slightly different. And it will be not like arbitrarily different. It will be offset from original color by the value equal to frequency of vibrations in this molecule, which somewhat related to what we see on the board. Make sense? Does it make general sense to everyone? Okay. And another thing which I promise we will have before the end of the course, and the thing that maybe you'll find connection to what Lolo is doing for research, Frank Condon factors and Stokes shift. Is it make sense? I'm really excited to speak about it. I just don't know if you have time. Can you say maybe briefly, what is stock shift and Frank-Condon?
So Frank-Condon principle has to do with when electron is being excited from the ground state to the excited state, and you have what's it called now?
Just generally.
Yeah, so it's some sort of energy of the wave function on the ground state overlapping with the energy of the wave function in the excited state.
Okay, yeah, very good, very good. So I'm about to go back to this math very soon, but thank you all, and I'll comment because she told everything correctly, but too brief as I act. When we have molecules that we excite by light by promoting electrons from ground to excited, there is an associated process when the potential energy surface in the excited state is slightly different. It may be have the same shape, but it could be shifted position, equilibrium position, and then the optical spectroscopy, absorption and emission, happen not literally on the energy difference between electronic states, but it accumulates additional offsets equal to the frequencies of the nuclear vibrations because of the quantum properties of the nucleus. Make sense? Whew. Okay, I hope it will work as a little motivation because when I was briefly reviewing the class material, it looked so boring to me. When about 10 years ago, I did design the course as for graduate students, where all the things are derived on the board. So lectures were longer. We were making pauses, and everyone was coming to board to derive things. And then it was kind of challenge to do exercise. But for this long derivations, there is a chance to miss the actual meaning for chemistry and physical chemistry. So through this our little consideration, maybe it cheers up our effort. So when we met last time, we got to this equation where this r squared comes from the Taylor expansion of the potential energy surface, and we keep only the quadratic term. And then we decided to do a straw man who tries to jump lower than the ground floor, and it's not possible. And to do this jumping on the energy levels, we designed or accepted the ladder operators up and down, and then we went through derivation where these ladder operators are expressed in terms of position and momentum, right? As summation, sum and subtraction, and momentum comes with imaginary part, and we found the coefficients to be placed here. After that, we did apply the annihilation operator to the ground state, and found out that it gives quite simple differential equation that we have solved by using this separating variables and integrating. And now we do have distribution of probability to find interatomic bond literally as a minimum, as an optimal bond length, a little shorter or a little longer, right? A little shorter, a little longer. And we have width parameter that defines how big is uncertainty of this position in case our oscillating bond stays in the ground state, which means absolutely zero temperature. There are no temperatures, there is nothing, but it's still uncertain. And we do have two directions to go from here. One is maybe even more. One is to revise the value of normalization, which we kind of touched, but it was too quick. And another, we can continue to solve time-independent Schrodinger equation for getting after ground, we get first excited, second excited, and we can use this philosophy of raising and lowering operator, just applying this operator. So instead of solving differential equation, we just apply differential operator and get next state. So if things develop favorably, then in 22 minutes, I want to arrive to this picture and this equation. You see it's not very major advance. Therefore, I use time for taking interviews. So the cyan line would be our outcome. And it differs from ground state wave function by factor r linear. So this Gaussian wave function is multiplied by linear function, and then on positive side it's positive, then it passes through zero, and then it's negative and approaches minus negative. Later on we will discuss the energies. I think we'll skip, but the ground state energy is 1/2 of the Planck constant and frequency, angular frequency of oscillation, and first excited is bigger than that by h bar omega, like 1 plus 1/2 plus 1 will be 3/2, right? Let's maybe, okay, I'll do easier part and give hard to you. Let me just look on this equation and discuss how we see what is this first excited state. What are there any connections, similarities, and differences from other wave functions that we got acquainted with during the course? So, do you see any connections to the particle in the box? So it's I'm going to ask Joe, and it will be a little exam for you. I'm going to ask you to draw in the air the ground and first excited state for the particle in the box. Can you please try?
Yeah, wasn't it like just like peaks, or no? It was
How many peaks for ground state?
As many number of states as there were.
So if state number 1 and wave function is sine of n pi x over n, right?
Yeah.
So can you draw in the air in the first state?
Kind of like this.
First state is only one peak. It's half period.
Oh yeah, right.
One peak. Okay. If it is second state, how many peaks?
That'd be 2 peaks.
Or if it is sine, it goes like peak and anti-peak, plus
Yeah.
and minus. Do you see any connections to what is?
Kind of both has a peak and an anti-peak.
So ground state has one peak. First excited has peak and anti-peak, right?
Mhm.
Okay. Yeah. Thank you. Everyone is okay with this, and so here is the similarity, right? For ground state, everything is positive if you do not take square the wave function only. For the first excited, it crosses 0 once, and here just offset by energy. Now, what about the range of definition for particle in the box, in infinite box? They are literally 0 at the edges of the box, right? And there is nothing apart. Here, they go and approach 0 infinitely, right? Would you agree that tails of this function for the first excited goes a little further forward and backward than the tails of the ground state. Or you don't see it from my ugly drawing. But please take my word, and later I'll try to prove it when we go to more higher states. So it is not sharply ended at the edge because there is no edge. And the energies, the wave functions for higher energy state will protrude to the larger extent of space. This feature will be needed when we speak again about Frank quantum. So this feature that wave function for higher states take larger space, which kind of makes sense. If you excite it, it should oscillate with higher amplitude, right? And this will be seen in this quantum solution. And this feature will give some consequences to Frank quantum features in molecular spectroscopy. Okay, so oh, there is even some text about it. Okay, good. So when we applied annihilation operator to ground wave function, we got 0. It was way how did we got it? And here I suggest to quickly revise the normalization. So if wave function is defined with precision up to a constant, then this factor n is unknown on one hand. On another hand, if we take this function with star and without star and integrate, it should be 1, right? Which means n squared and this, since it is a real wave function without conjugation, we just multiply nominator by factor 2. And if one takes this integral, the integral of Gaussian function is square root of pi, and then one can find the 1 equals result of this integration, and then one inverts, solves it first for n square just by flipping stuff that were here under root. So m omega comes to numerator, Planck constant, and pi to denominator. But this is a solution for normalization factor squared. If we need normalization factor for a function, one needs to take square root of the square root. So this frequency and mass in the numerator, pi and Planck constant in the denominator, and then power 1/4, which is a square root. Okay. So this is fully processed ground state of the harmonic oscillator. And on the harmonic oscillator, we can always track back and plug parameters like frequency and mass that would correspond to broad range of examples. It could be different interatomic bond or oscillations, simultaneous oscillations of several atoms in a big molecule, or it could be plasmonic oscillations of electronic cloud in nanoparticle, and many other things. Okay, so we are applying this raising operator to ground state function, and we are going to get the first state function times some coefficient. So in order to do so, we use the phi naught ground stable function and then replace momentum with its quantum definition as a derivative over over position. And if one does so and takes care of the constants and imaginary units, yeah, maybe let's do this exercise. I don't know if you really need it, but it will be more vivid compared to just watching slides. So what should I, if I want to do this exercise, what should I care about and what can I neglect? So the normalization factor in front of wave function and normalization factor in front of operator can be left away for time. And if I need to look on them, I think the mass and frequency may flip to the denominator, because here is mass and frequency squared if we put here root of the fourth power. But additional mass and frequency may come from this factor and then from taking derivative. So it's better to process it later. So most important thing is the factor mass times frequency times position, and then here we will have derivative times Planck constant, and let's find what will be the sign. So I times one I will come from definition, another I comes from here. Their multiplication gives -1. Another -1 comes from definition of momentum, and another -1 comes from here. So I think there should be -1 should be kept. So omega minus h bar without square ddr e, and here what I remember for sure that should be r squared, and in order to put right coefficients I need to flip back and double check. So m omega 2 h bar. So first we will get the mass and frequency times absolutely the same function. I missed most important thing. There was r here, right? Okay, so m omega times r e minus m omega 2h bar r squared minus h bar, and then we need to take first derivative of this exponential. So how do we do it? Huh? Yes, keep it the same, but times derivative of the power, right? And derivative of the power will be coefficient will be repeated, and then we need to take derivative of the r squared, right? So to r, and then repeat the function minus m omega 2 h bar r squared, and close the bracket. So what do you see? Do you have any observations? So we do have two terms. Each of them has exponential, which is absolutely the same and can be placed out of brackets. And what is the power in front of this exponential? Is there any polynomial? And polynomial of independent variable r. 2 and 2r, right? Is it the same power, different powers for these terms? Yeah, same power. We have r here and r there, so it is polynomial of the same power. So I think we can just combine it, put everything in bracket, and it will be actually one term. Let's check what about the factors. So we have m omega here, m omega there. Then we will have this h bar here and here will cancel, cancel. So we will have m omega and m omega. We'll have r and r, and we will have exponential and exponential, right? So and the minus times minus will be plus. So we'll have whatever I skipped originally, then factor 2 because they are identical, and we have m omega r exponential minus m omega 2h bar r squared. Basically, that's it for the lecture. I probably have a couple of slides where it is written in a better typing, but and one also needs to normalize it. But this operation of taking derivative, if we are deprived from computers and textbooks, if we are on the inhabited island, is noticeably quicker and simpler than solving differential equation. To get the next excited state, we need to continue this exercise and just apply creation operator once again. There is a way to prove that this is correct solution, as we always do proof in math. Just take this wave function, plug it into Schrodinger equation, and make sure that it doesn't violate anything, that we'll get left and right part equal to each other. But I certify it will be correct. So multiplying r by Gaussian function will have this plus and minus that we have already discussed. There is also normalization constant, and let's check what I was doing last year. Maybe normalization constant is postponed to the next meeting. So since we have a couple of minutes, let's look how the votes develop. So Ellison and Adam didn't vote, and then we'll chop section so that there will be chance to talk for Lola. So yeah, many thanks for votes. We will process and do it if no one objects on November 5th. If there will be big motions and you vote and suggest other day earlier, I will be happy and responsive. Later, no. Earlier, yes. And just for your curiosity and understanding, they all are equally important, and for completing practical parts of the projects that we will be likely doing, the this section is more important. But for answering questions of the audience, the first half is important, and especially number one. So thank you, Wade, for selecting it. So you probably will be the first speaker, and you'll save others if well. I will ask once again if instead of mini projects anyone wants exam, but I hope, well, not hope, it's up to you guys, but I anticipate that you will vote for projects. And the projects will be big event where you report your research and there will be visitors. And all previous years, visitors were asking not about results of research, but about how the code is working. Basically, what we will do in private on the next meeting, but what major visitors will miss, and they will, if Wyatt is voting to discuss section number one, maybe on the public event, you save the class by raising hand. I want to answer this question, because the question how the code is working will be asked to everyone. It's not my wish, it just happened in the past. And what else? Enough. Thank you for being here. Let me know if I can be helpful. Meeting is done. Everyone is welcome to disconnect. I'll stay here to answer any questions online or in person. No questions from online.